In this video, I'd like to look at some example problems for finding the modulus or the absolute value of different complex numbers. And with this problem, we need to consider the complex numbers that are plotted below. And the question asks, which of these complex numbers have a modulus of 5? And remember that modulus, also known as the absolute value, is essentially just asking how far is the complex number from the origin, from this point right here. And you can see, for instance, that this point C right here, since it's on the imaginary axis, this is actually 5 units away. We could use the formula to confirm this, but you can visually see that this would have a modulus or an absolute value of 5. So C is definitely one of our answers, but for the other ones, we will need to calculate what the modulus is for each of these. And in the last video, we derived a formula where if we have some complex number z equal to a plus I times b, where a is the real part and b is the imaginary part, then its modulus, its absolute value, is equal to the square root of a squared plus b squared. And you get this if you actually draw a line between the complex number and the origin and decompose that line into a right triangle, and then use the Pythagorean theorem to actually solve for this absolute value. Since this right here, this length, this would actually be the absolute value of a, and we could set up that Pythagorean theorem using this length of 3 and this length of 4. But the formula makes it so that we don't have to draw a picture when calculating this modulus for each of the points. And for A, we can see we have actually a 3, 4, 5 right triangle, but let's confirm that with the formula. We'll look at the absolute value or the modulus of A, and we can see the real part is 4, which means we have 4 squared, plus the imaginary part, which is 3 here, and we'll square that. 4 squared is 16, 3 squared is 9. Adding those together, we get 25, and taking the square root of 25, this is equal to 5. And we can see that A also has a modulus of 5. Now, looking at D, we can find the modulus of D by considering the components. Since the real part of D is also 4, so we have 4 squared plus the imaginary part of D, which is -3, and we will square that. And 4 squared we know is 16. -3 times -3 would be +9, and we end up with this exact same scenario, meaning we have root 25, which is 5. And D also has a modulus of 5. And at this point, we just need to check B. So let's plug that into our formula here. We want the modulus, or the absolute value of B, and it has a real part of -5, and we'll square that. It has an imaginary part of 5, so we'll add that and square it. And -5 times -5 is 25. 5 times 5 is 25, so we get the square root of 50, or really we get twice 25 underneath the radical sign. And we write it like this so that we can separate this into 2 square roots. We have root 2 times by root 25, and the square root of 25 is just 5. So this is equal to 5 multiplied by the square root of 2, meaning that the modulus of point B is actually longer than 5. So B is not one of our answer choices, but these three here, we can feel confident that the modulus of each of these points is equal to 5. And let's look at one more example problem. In this problem, we need to find what is the modulus, or the absolute value, of the complex number -24 minus 7i. And we want an exact answer that is expressed as a radical, or as a whole number. So let's paste in our formula for finding the modulus, where again, if we have some complex number z, that's equal to a plus ib, then the modulus, or the absolute value of z, is just the square root of the real part squared plus the imaginary part squared. And for our complex number, we can call it z1. This is equal to minus 24 minus 7i. And we can see that the real part, or a, in this formula is minus 24. The imaginary part would be negative 7, meaning that if we take the absolute value, or the modulus, of z1, we get the square root of a squared, or minus 24 squared, plus b squared minus 7 squared. And minus 24 multiplied by minus 24 would be positive 576. And minus 7 times minus 7 would be positive 49. If we add these together, we get the square root of 625, which is actually a perfect square. This is equal to 25. So the distance that this point is from the origin is 25 units, and we call that distance from the origin the modulus, or the absolute value of the number, meaning that we can put 25 into our box here.